Okay, sorry about the interruption. Kids are fed and driving around with their dad who's taking a speaker conference call. So they should be gone for a while, which means we can finish up this lecture. So when we left off in part 1, we were looking at the load in the steel and the load in the concrete for a column that was a combination of both materials with different areas. And we saw that it was a combination of area and stiffness that impact the percentage of load they take on. So it's not always obvious which one is going to take more load. So we had already figured out what the combined stiffness and area of steel and concrete was, and then the total stiffness based on stiffness of the material and the area of each material for the entire system. And with that, we can figure out what the load in the steel is relative to the whole system. So F is our placeholder for the force in the system. We don't know what it is, so we're using F as a placeholder. And we know that the combination of stiffness and area for the steel was 1.04 times 10 to the 9 newtons. And the system as a whole was 1.57 times 10 to the 9 newtons. And when we calculate that, we get 0.662 F. Remember, F was just a constant that's representing the entire force. Now, for those of you that understand ratios really well, you can probably figure out that it's about 33% left that is going to go to the concrete portion. But let's go through the math and see anyway. F of the concrete is going to be F of the system times the EA of the concrete divided by the EA of the system. We don't know what F is, so it's just a placeholder. We do know that the EA of the concrete was 0.531 times 10 to the 9 newtons. And the system as a whole is 1.57 times 10 to the 9 newtons, leaving us with 0.338 F. So and you can see that it's unitless, and F would be the placeholder for the units. So if our force is in newtons, it would be 33.8 F newtons. If it was in kilonewtons, it would be 33.8% of the force in newtons. So we could also write this as the force of the steel in the steel is 66.2% of the total force. And the force in the concrete portion is 33.8% of the total force. So we can see that we can break it down, and if we knew what the force was in the system, we'd be able to see exactly what load is in each portion. And with that, if we knew what the strength of the steel was, which we do, and if we knew what the strength of the concrete was, which we'll learn next week, we'd be able to see if each portion is strong enough to hold its portion of the load. But to do that, first we need to know how much load is in each part, and then we can start thinking about the capacity of each part. And so that would be the next step. But this was just to show you what load sharing looks like. And so you can see here, here's the same thing, worked out step by step if you weren't able to see it or follow along. But I like to work it out in real time and have you hear me talk it through, because sometimes it's just nice to hear a voice talking it through. Sometimes, if we don't want to keep it as two separate materials when we're doing the calculation, sometimes what's easier for us kind of mentally to get our head around, is pretending one of the materials is the same as the other. So we saw that the area and the stiffness were different, and it made it really hard to figure out which one of those two things was going to govern. But what if we said that the only thing that was different, potentially, was the area? And we equated the appropriate area of steel if it was the same stiffness of concrete. So basically, let's take the steel out, see what equivalent concrete would equal that steel for area and stiffness, and then add that back in, and it might make things a little bit easier. Now, I'll show you how we do it for something simple like a column, and then next week it's going to be handy because that's how we treat steel in a concrete beam for bending. We often put the steel very low in the beam in that tension zone because we know concrete can't take any tension, and we'll pretend that that steel is just like concrete, but we draw it with the equivalent area of as if it was concrete. So I'll explain all that next week, but we need to understand that concept before we get to that. So when we do that, we call it transforming the section. It sounds very fancy. It feels like it should be something from Star Trek or something, but really we're just pretending one material is like the other. So if we know that the stress is equal to the force divided by the sum of the combined stiffness and areas, so any object of any material or any combo of material will act the same as long as the sum of the EA is the same. If we have this EA of 1.57 times 10 to the 9 MPa, we could do either of the following. We could say EA or E is 1.571 times 10 to the 9 MPa and A is 0. Or we could say the E is 1 MPa and the area is 1.571 times 10 to the 9 millimeters squared. These two things multiplied by each other still equals that combined stiffness, and these two things multiplied by each other still equals that total stiffness. Now, I'm not saying we wouldn't literally change these things. It's just a conceptual thing that allows us to possibly make our calculations a little bit easier. Seems kind of baffling when I show it like this, but let me keep going and I'll explain what that means. The area of the transformed section is equating this N times the area of the other material. We often do steel, so I've included an S there. But N is just the ratio of steel to concrete stiffnesses. And then all we're left with is an equivalent area. Or we multiply that steel times the ratio of stiffness between steel and concrete, manipulate our steel area, and we'll find out the transformed area of the steel. Again, this one's best described with an example. So let's take a look at that same first example that we had. And for this example, we knew that our area of steel was equal to 5,210 millimeters to the squared, and the E of the steel is 200,000 MPa. The area of the concrete we already figured out was 17,689 millimeters squared, and the E of the concrete is 30,000 MPa. And we want to look at this column as if it was all concrete. So we want to see what equivalent concrete would represent that steel. So the concrete that we already have, that's going to stay the same. That's just fine. But what we're saying now is for this area of steel, if we took it away and found the equivalent EI combination or EA combination that would allow us to rewrite it as if it was concrete. So let's take a look at how we do that. The area of the transformed section, changing steel to concrete, is N, and N was ES divided by EC, times the area of steel, or 200,000 MPa divided by 30,000 MPa times our 5,210 millimeters squared. And when we write this out, we get a transformed area of 34,733 millimeters squared. So that's taking the steel and pretending it's concrete. So if we had 5,210 millimeters squared of steel, that was 200,000 MPa, it's the same thing as 34,733 millimeters of concrete with an E of 30,000 MPa. So as long as we switch that E over, that's the equivalent amount of concrete that we need. And that's saying that our effective area now is the area of our concrete plus the area of our transformed section, or 17,689 plus 34,733. Our effective area becomes 52,422 millimeters squared. So if we wanted to pretend that this amount of steel was actually concrete with the same stiffness of the concrete that we already have, instead of having 5,210 millimeters squared, we would have 34,733 millimeters squared, giving us a combined total of 52,422 millimeters squared. If you wanted to look at it graphically, what we've said is we've taken that amount of steel and pretended that it's concrete with the same stiffness, so that now we can treat this as our column. And in some cases, that's going to make life a little bit easier. Now, there's a thing we've forgotten about this. This was talking about a column. What's the thing in columns that we always have to worry about if they're any amount of height at all? We have to start worrying about buckling. We intuitively know what happens. We know when it's really, really short, it's all about strength. But as things get taller, they can be governed by buckling or some combination of the two. So this is really just talking about area and strength alone, and we'd have to do something else for buckling. And that is something that we'll talk about next week when we look at concrete columns. So I just added a note for that there. So let's do another transformed section. We have a 250 by 350 concrete column that has an E of 25,000 MPa, so this is a different batch of concrete that has a different stiffness, and it has 8 20M bars. Now we're going to talk all about the lexicon for concrete columns and beams next week, but what this is saying is that we have 8 pieces of steel in it that are about 20 millimeters in diameter, not radius, but diameter. And we want to know what the transformed section of this member is. So the first thing we have to figure out, let me draw this for you here. That would be 250. And that would be 350. And we've got 1, 2, 3, 4, 5, 6, 7, 8 bars in that. So let's figure out what the area of steel is. The area of steel is going to be 8 times the area of each one of the bars, which is 20 divided by 2 squared times pi, and we're going to get 2,512 millimeters squared. And we know that the E of steel is 200,000 MPa. Now, let's talk about the area of the concrete. I'm going to do 250 by 350 equals 87,500. If I wanted to be really thorough, I could take this 87,500 and minus the 2,512. Definitely we could do that, and it would certainly be more right. Because often what we're doing is trying to find the ratio. You can see that it would have a very small impact on it. It makes a difference for sure, and if we were at like 99, I don't have my calculator here, if we were at like 99% in our final design, if we were so close to working, or we were on 1% over, so that our CF was just a little bit bigger than our CR, this might be something we'd want to look at. But we don't know if this is the right answer or not. We don't even know what they're asking us for. The industry standard is don't remove the area of steel from the area of concrete. It's not wrong to do it, but it's an extra step that has very little impact on the final design. So we tend not to do it. And that's how I'm going to do it from here. If you decide to do that in your assignment, of course that's participation mark, no problem there. In the exam, this is the way I'm going to do it. So you might be more right, technically, but it's not the way anybody does it, so we're going to stick with doing it this way, okay? So we have the area of and stiffness of the steel, and we have the area and the stiffness of the concrete. They gave us the stiffness right in the question of 25,000 MPa. And we know that the transformed section is the area of the steel, or sorry, the stiffness of the steel divided by the stiffness of the concrete times the area of the steel, or 200,000 divided by 25,000 times our 2,502. We calculate that and we get 20,096 millimeters squared. So what we're saying is this concrete column with 8 20M bars that are all sharing the load equally is the same thing as a concrete column that has steel and concrete working together. That would be similar to an entirely concrete column with a total area of 87,500 plus 20,096 equals 107,596 millimeters squared. So this is the same thing as an entirely concrete column that's just a little bit bigger. If I had my calculator right here, I'd calculate exactly what that is. We could figure it out as a square, we could square root it and figure it out as a square. Regardless, we can figure out what the equivalent area would be if we pretended that entire thing was concrete. So I have that fully worked out here. So now let's talk about the fun part, composite systems. So composite is different than sharing the load. A composite system is if two objects or materials are combined so that they support the load as one thing. The steel and concrete were working together, but they weren't acting as one combined uniform piece of material. Composite systems ensure that the things act as one solid piece, and I'll show you why that's so important. And in the final lecture, when I do beam testing, I'll show you, you'll actually visibly see the difference between those two things. But here's the trick. The materials must be bonded so that they don't slip relative to each other. So what does something like that mean? Well, first, in axial loading, it doesn't really mean much. But in bending, we need to make sure shear can be transferred across the plane where the materials interface. What the hell am I talking about? Well, I'll show you in just a second. Here's the interesting part. They can be two different materials, like the example we just did, or it can be two pieces of wood, like for example, a glulam beam. I'm going to do some math next, or I'm going to use an example where I'm going to use two pieces of wood, mostly so that we don't have to muck around with different stiffnesses. But we'll talk about two pieces of material that have the same stiffness, so the only thing that can change is their shape properties. Remember, all of our shape properties are area, which apply to axial and shear loads. We have our section modulus S, which applies to bending, and we have our moment of inertia I that applies to stiffness of the member. So we need to, we'll get rid of the having to worry about stiffness of the materials and use all of the same material for the next round of examples we're going to talk about. So composite versus non-composite, or what we call shearing. For bending elements, longitudinal shear is critical. What does longitudinal shear mean? That means any plane where there's interface has to be glued together so that they can't slip this way relative to each other. So normally for shear, we're talking about shear in this direction, but we're going to be talking about longitudinal shear. We're not going to calculate it, we're not going to worry about it too much, but we want to make sure that we're able to ensure that there's no slip along the latitudinal or the longitudinal shear plane. So if we allow them to slip relative to each other, we'll only get load sharing. If we glue them together and force them to act together, they won't slip relative to each other and we'll get one large member. So let me talk about an example with that. So we're going to go through and we're going to look at two 140 by 140 timber beams spanning some unknown distance. But before I do that, I want you to think about something like I always use a phone book as an example, but you guys probably have never even looked at a phone book. If I bend this like this, you can see that the edges here move relative to each other. When I bend this, all of these pieces of paper slip relative to each other. We get almost an infinite, or every single page is allowing slippage from the other page. If I took that same piece of paper, that same booklet, and I glued every page together and let all the glue dry, when I tried to bend it, it would be much harder to do. It's not that the glue itself is adding any particular strength to the system, but it's that it's not allowing any longitudinal slip between the two surfaces. So we've bonded them together. And I'll show you. If we take those two 140 by 140 pieces of beam and just let them sit on top of each other, we don't glue them together, when we bend them, we'll get a shape that looks like this. And these two things will actually be a difference of dimension at the two ends. Essentially what we have, there's our stress profile. We've got two elements with that stress profile. We know that we can take this or bend this amount right until that and that and that and that, where the extreme fibers reach the maximum stress that we can see. So if this was an SPF beam in bending, It varies, but it's somewhere between 7.5 and 11 MPa of stress that we could see at that maximum point right there. What's interesting here is that we have two neutral axes. Each one of these has a neutral axis. If we glue them together, we end up with only one neutral axis, and we have our maximum stress at the top and the bottom, where our extreme fiber is, and that can go all the way up to the maximum stress we could possibly see. So visually you can see what's happening, but what does that mean? I'm going to go through and I'm going to show you mathematically some implications of that. So there's our non-composite and our composite with our maximum stress. So for the 140 by 140 beams of the same material stacked on top of each other, calculate the shape properties for axial load and shear, bending moment, and stiffness for the non-composite and composite member profiles. So let's take a look at what that looks like. So what we're saying is, we have something with a B of 140 and two separate beams stacked on top of each other with a D of 140 each. If we glue this together at that center line, we're saying we have one beam that has a B of 140 and a D of 280. So we're using the same amount of material. All we've done is we've glued that center line between the two of them. We've glued them, there's a calculation for it, but that's way beyond what this course is. And it's surprisingly not that much glue. We have to be able to prove consistently and statistically what that is, but it's not that much. And we want to look at area, section modulus, and I for both of these systems. So let's look at the area for shearing. It's 140 times 140 plus 140 times 140. We calculate that and we get 39,200 millimeters squared. Well, what's the area if we make it composite? We've got 140 times 280. We calculate that and we get 39,200 millimeters squared. Well, that doesn't seem very exciting. The area for composite equals the area for shearing. That doesn't seem that impressive. And we know that area is used for both axial loads and shear loads. Well, it doesn't seem like we get much advantage from making it composite. So if we have things in shear or in axial load, so that's tension or compression, making it composite doesn't give us much advantage. We can share the loads if we feel like it. Let's take a look at the S of shearing. We're essentially saying we have two beams that are 140 by 140 squared divided by 6. Remember, for a rectangle, S is BD squared divided by 6. So we calculate this and we get 0.915 times 10 to the 6 millimeters squared. And let's look at S for composite. We get 140 times 280 squared divided by 6. We calculate that out and we get 1.83 times 10 to the 6 millimeters squared. So you can see that when we glue them together and make it act as one deep beam, we get a much higher S. In fact, for our rectangles here, our S composite is 2 times the S of shearing. So they were equal for axial loads or for area, and we get 2 times the effectiveness if we make it composite. Let's do the I for shearing, or our moment of inertia. We know that it's BD cubed divided by 12. We have 2 of them, so we have 140 times 140 cubed divided by 12 plus 140 times 140 cubed divided by 12. We can calculate that out and we get 64 times 10 to the 6 millimeters to the 4th. And then let's do I composite. It's going to be 140 times 280 cubed divided by 12. And that is 256 times 10 to the 6 millimeters to the 4th. So I composite equals 4 times the I of shearing. So you can see that when we have things in bending, which is governed by either bending or stiffness quite often, being able to take small pieces and glue them together and make them composite is highly effective in dealing with bending stress and stiffness problems. So it's something we really like to do if we can do it easily. So here that is worked out. So there's a real advantage for us in making things that are in bending act in a composite way. So what are some examples of that? Well, our concrete on metal deck is a really good example. Remember last term I talked about the only difference in the metal deck between concrete on metal deck and just plain metal deck is that they punch these little holes in the side. Those little holes are all about grabbing on to the concrete. So they're not big enough that the concrete can flow out of them, but they are big enough that when the concrete cures around it, it is bonded to the steel essentially. Not on a molecular level, but on a material properties level. And so our steel is at the bottom where something in bending is often in tension. And we have concrete on the top where concrete behaves really well in compression. So composite on metal deck is a really useful way to make use of composite systems. The added bonus is that the steel becomes the formwork for when we're casting that concrete. We can take our concrete on metal deck and make it composite with a steel beam below. It's a little bit hard to see here. But that is an I-beam. And these are studs. So what this is showing is just a little cutout section where sometimes what they'll do is before they pour the concrete, they'll put the steel deck down on the steel beam and they'll shoot studs through it. And then when they cast the concrete around it, the studs then actually start to act composite with the beam itself. And so what we end up with as our composite beam member we actually get some of that concrete on metal deck acting as part of our beam system. Now, it's really effective in some places where there are slightly different governing loads. In Toronto, most of the times we're governed by vibration, and this does not deal with a vibration issue very well. It doesn't really grab the complexities of vibration. And so often I have found that if you specify this for strength and stiffness, when you go through and do the vibration check, you need to beef up your steel beam anyway, which means it would have worked for strength and stiffness even without making it composite. So why spend the extra time and cost making it composite if you don't need to? I've only ever had one project where this has actually been of value. I've actually had value engineering propose that we do this on several projects, and we've had to go through and prove to them how it wasn't that effective. Now, there are times and places for it, or maybe you have a project where vibration just isn't a concern at all, but most of the projects I'm working on tend to be governed by vibration. So it's a handy thing to know you can do, but just be aware it's not always a useful thing. The systems we were talking about in wood beams and studs last week, so specifically joists and studs last week, where we talked about the plywood trying to pull down and engage these elements, we can also just treat it as if it was an effective section, or that we've made it composite. We've made this plywood composite with our joist, and we're taking a little bit of that plywood and making it be a beam for us. Our wood sections, our composite eye joists, when we glue in here, it's actually composite two ways. These elements here are often made of OSB, which is glued together, but that element's mostly for shear. And the shear elements we know are governed by area, and load sharing and composite action, area is the same. It doesn't really have an impact. But they are glued together, so they would effectively be able to act as composite, but it doesn't really get us much. Our top and bottom chords are glued to our web, and that, as long as we can get our longitudinal shear transfer along those joints, which means lots and lots of glue, we can have this act as a composite section, rather than just a block at the top and a block at the bottom and a piece of plywood in the middle. We can actually make it act composite. SIPs, or structurally insulated panels, where we have plywood on top and plywood on bottom, and then we have, in between doing all the work of shear, is some rigid insulation, and all of those are glued together. So we have to be able to make sure that that insulation is strong enough to carry both longitudinal and regular shear, and we need to make sure all of these things are glued together to transfer longitudinal shear. SIPs are really great for prefab houses, I found. You can use them in some bigger places, but we're limited by the size of the plywood, which is 8 by 4. You can get 4 by 12 sheets in some places, I think, and probably custom you could get bigger, but it starts to be really expensive to do anything custom. Interesting side note, ants love the insulation in SIP panels. So if you're doing it close to the ground, just be aware of that. I think you can buy special insulation that they don't love to eat, but if you're in a place that has lots of ants, it's just a good thing to know about. We had that happen actually on Bridget and Howard, or Shim Sutcliffe's, their own personal cottage, so that was lots of fun. Composite systems, we can also do flitch beams. So flitch beams is where we say, our wood beam alone isn't cutting it. Our entire project is a wood project. We don't want to switch to just a steel beam. We could make our wood beam bigger, possibly, like this, and add extra plies. But what if this is our wall? Well, it now doesn't fit in our wall. So in cases like that, we don't want to add a steel beam that's switching trades to like do all of the connections. We have a trick up our sleeve. We can make it a flitch beam. It still involves some steel, but it's not as much steel, and the wood is doing a lot of the work at the ends of the beam. And so what we do is we just put small plates of steel in the middle, and we make sure they're screwed together in such a way that we can transfer any shear through them. And if we do that, these two are equivalent stiffnesses. So they would both take the same amount of load and stiffness. So these two things are equal from a design perspective, but you can see that we've made the width a lot less. Now, a lot of times our walls will be 2x6 stud walls. So that means 5.5 inches for stud with plywood on each side. And maybe we just notch out the plywood a little bit locally to fit the beam in. So that can be a really effective thing to do when we want to have a wood project, but we're just shy on 1 or 2 beams. I wouldn't recommend it for an entire project, but it can be helpful where we've kind of got ourselves in a sticky situation. Glue-lam beams and girders. Their entire kind of concept is to be composite members. We actually have it right there. The glue is right in the name. They're glue laminated systems. And so what we've got is stacks of 2x4s or 2x6s on top of each other, gluing each plane together. So we've got a series of them, and each one of these joints, we've got glue making sure they're bonded together, transferring that longitudinal shear, making them, instead of act as 1, 2, 3, 4, 5 individual 2x6s on flat, we've got one large member. This is the great thing about doing it in laminated sections. Trying to curve something really deep is really hard. We're limited by the radius that we can curve is dependent on its depth. So deeper it is, the less radius we can have on that curve. But because glue-lam is made up of a series of shallower beams, essentially, we can pre-curve the individual beams and then glue them together, essentially giving us a much deeper beam with a tighter radius. And you can see you can get quite a tight curvature if you want to. CLT, same thing. We are gluing pieces of 2x4s or 2x6s together to make it look more like plywood. Plywood's a composite section as well. What are some of the more advanced composite systems? I mean, these are way beyond this course, but things like Kevlar or carbon fabrics that we would glue on to existing structures because they're really strong in tension. So why wouldn't we just make our whole system out of that? Well, they're really prone to buckling, or they're not stiff in bending. But we've seen that anything in tension can often behave very easily. So where we have things failing, like the underside of concrete when it's in tension and we get concrete spalling off, we can glue these to the underside. That means we don't have to maybe demo and replace the piece of concrete. We can put a patch on it, at least for a while, making it act composite and increase the life of it. And that's what we see happen a lot in older structures that are maybe past their lifetime. So what are our takeaway tips? Load follows the stiffest path. Load sharing is additive. Composite action can technically makes a member bigger versus just load sharing. Longitudinal shear is required for composite action in bending. You should be able to calculate load sharing in a column. You should be able to calculate a transformed section. And you should be able to tell the difference between load sharing and composite action in a beam or in stiffness. And you need to be able to identify those and calculate them for a rectangle. So this was our first go at doing the project online. I'm going to post this video and I'll let you know when it's up there, which you'll already know as you're watching this and I'm hearing it in real time. But I'll set up a means for you guys can communicate to me any feedback. I mean, we only have one more real lecture left. Next week, we're going to be talking about concrete columns and beams. And then the last lecture is going to be me just destroying a bunch of beams. Mostly I get to have fun. You'll get to sit back and laugh at me pop yourself some popcorn, print out the sheet I'll provide you, and keep track of any information. I'll need somebody here with me. I'll figure out how to do that and have somebody watch my kids, but I'll make that work for us. And I'll follow up more about the exam and if I have any difficulties. So this was a great kind of first go at it, and I'll see you guys next week.